In this lesson, we will learn how to calculate the volume of a pyramid and to use the formula that we derived to solve problems involving volumes of pyramids. Okay, but before we talk about the volume of a pyramid, we need to have an understanding of how a pyramid is defined. So a pyramid is a polyhedron formed by a polygonal base and triangular lateral faces that meet at a common point called the vertex of the pyramid. What that essentially means is if you want to construct a pyramid, you start with the base. Now the base can have any number of sides. This particular one has 4 sides, so it has a quadrilateral base. Now you could easily have a base that's a pentagon, a hexagon, so on and so forth. So you can choose the base at will. And then what you do is you choose a point that's not in the plane of the base, so a point that's either above or below the base, and then you connect that point to all of the vertices of the original polygon that you chose for the base. Then, notice I would have created what we call a pyramid, with the point that we chose being the vertex of the pyramid, and all of these triangles on the sides are called lateral faces of the pyramid. So before we start developing a formula for the volume of a pyramid in general, what we're going to do is first we're going to consider a segment AB with a length b and a line L that's parallel to AB. And let h be the distance between AB and line L. So here's the distance between those two, between the line and the line segment. Okay. Then what we're going to do is we're going to choose a point C that's somewhere on the line L, and we're going to draw in the triangle ABC. Okay. Now, if I wanted to calculate the area of such a triangle, I would need to know its base and its height, because the area formula is 1/2 times the base of the triangle times the height of the triangle. Okay, so the area of this triangle ABC would be 1/2 times the length of this segment AB times the height of the triangle H. Now if we choose a different point C on line L and we draw in triangle ABC once again, notice that the area once again is going to be 1/2 times the length of the base, which is the same length of the base of the triangle from the first slide here. Okay, so these two triangles have the exact same base. Not only that, but they have the same height, even though we chose a different point C that's on line L. So what we can conclude is in general, if two triangles have the same base and the same height, then they're going to have exactly the same area, since as a matter of fact, that's all that goes into the calculation of the area of a triangle is the sides B and H. Now consider a three-dimensional figure that's similar to the situation we just explored. So suppose you're given a polygon like this, okay, and a plane R that's parallel to the plane containing this polygon. Notice you can form a pyramid by choosing a point in the plane R and connecting it to each vertex of the polygon. What do you think is true of all pyramids formed in this way? Okay, so this postulate is going to help us develop a formula for the volume of a general pyramid, and it states this: that pyramids that have equal base areas and equal heights have exact same volumes, have identical volumes. So any two pyramids that have equal base areas, that doesn't necessarily mean they have the same base shape, but as long as they have the same base areas and equal heights, then they're going to have equal volumes, just like as we showed is true for two triangles that have the same base and same height. The same thing applies to pyramids. If two pyramids have the same exact base area and the same exact height, then they're going to have the exact same volume. Okay, before we tackle the problem of finding a formula for the volume of a general pyramid, we need to find a formula for the volume of a wedge pyramid, such that the one is shown here, like the one that's shown here. Okay, so a wedge pyramid is basically a pyramid in which the base is a triangle and a perpendicular segment from the pyramid's vertex to the base intersects the base at a vertex of the triangle. So I refer to this wedge pyramid as pyramid A-BCD. The reason I refer to it as A-BCD is because in my notation I would like to be able to tell which point refers to the vertex of the pyramid. So this is the notation that we're going to use throughout this lesson. Now to find the volume of this wedge pyramid ABCD, we first let the area of the base BCD be represented by the symbol B. And we're going to let the height of the pyramid AD be H. So the area of this base is big B, and the height of the pyramid is AD, which we're going to refer to from now on as H. Okay, so what we're going to do is, out of this wedge pyramid, we're going to construct a triangular prism. Okay, now the edges EB and FC, we're going to make it so that they're congruent to AD, the height of our original wedge pyramid, and also parallel to AD, the height of our original wedge pyramid. Okay, we're also going to construct this prism so that the bases are congruent, so that EFA is congruent to the base of the original wedge pyramid BCD. Notice that by constructing this triangular prism in this way, it allows us to write the volume of this triangular prism in terms of the base of the wedge pyramid, B, and the height of the wedge pyramid, H. So the volume of this triangular prism that we created is just the area of the base of the original wedge pyramid times the height of the original wedge pyramid, H. So in the end, when we come up with our formula for this wedge pyramid, you should be convinced that it's going to be less than the volume of this triangular prism. Now it should be clear that the volume of the wedge pyramid ABCD is less than the volume of this triangular prism that we created. But how much less is it? Well, to figure this out, the first thing we're going to do is draw in the line segment from the point E to C. Since this is the diagonal of a rectangle, okay, notice that the reason I know this is a rectangle is because I constructed EB and FC to be congruent. Okay, not only that, but I know that these are right angles. By construction, I know that these are right angles. Okay, so basically what I've done here is by drawing in this line segment EC, I've created two congruent triangles. So by drawing in the diagonal EC, you'll notice I've created two additional pyramids that are separate from my original pyramid ABCD. Notice I've created a pyramid AEBC. Okay, so here's the base of that pyramid I just referred to, and the pyramid ACFE. Now notice that these two pyramids are going to have precisely the same volume. The reason is because notice first of all that by drawing in this segment EC, I've created two congruent bases for our pyramids, two triangular bases that are congruent since this base here was a rectangle. Okay, so I know at the very least they have two congruent bases, these two pyramids. Not only that, but they have a common vertex in the point A. So using our postulate from before, these two pyramids have the exact same volume because they have the same base area and the same height. So let's take a look at the pyramids, the two pyramids CEFA. So I'm talking about this pyramid here with the vertex C and the base EFA. Okay, so here's the base of that pyramid and here's the vertex. And let's look at the original wedge pyramid and let's compare their volumes. Well, we constructed this triangular prism so that EFA, the triangle, would be congruent to triangle BCD. Okay, so I know that at the very least they have congruent bases. I'm trying to establish that they have the same volume. So I try to see if they have the same base area, and they do in this case because I constructed it to be that way. And notice that they also have the same height, okay, because this height FC I constructed so that it was congruent to the height of AD. So that's the reason these two pyramids have the exact same volume. So what we just shown is that by forming this triangular prism, we've essentially formed three pyramids that have equal volumes. Okay, so basically what we're going to do now is we're going to compare the volume of our wedge pyramid that we're trying to find a formula for, okay, and the volume of the triangular prism as a whole. Okay. So the first thing we're going to do is we're going to write the volume of the pyramid ABCD, the original wedge pyramid, in terms of B and H. That's our goal. Okay. Well, if you notice, since each one of these pyramids inside of this prism are congruent, okay, and there's exactly 3 of these pyramids, then it only makes sense that the volume of our wedge pyramid, ABCD, is 1/3 the volume of the entire triangular prism. This can be expressed in this way. The volume of wedge pyramid ABCD is just 1/3 times the area of the triangular prism, which we already said is equal to the base of the prism times the height. So now we have the formula for the volume of a wedge pyramid. Okay, so as a reflect exercise, explain how you know that the 3 pyramids that form the triangular prism all have the same volume. Okay, so now that we know how to find the volume of a wedge pyramid, we can extend this idea or incorporate it when we're finding the volume of a pyramid in general. Okay, so in the Explore we showed that the volume of any wedge pyramid is just 1/3 the product of the base area and the height. Now let's consider a general pyramid like this one shown here. Notice that any general pyramid can be decomposed or partitioned into non-overlapping wedge pyramids. Okay, for example, notice here we have a pyramid that has a quadrilateral as a base. Okay, and also notice that this pyramid here that has a quadrilateral as a base can be decomposed into non-overlapping wedge pyramids, exactly 4 of them, as a matter of fact. If we draw the perpendicular from the vertex to the base, we make these 4 wedge pyramids here. So the volume of this pyramid as a whole, is just going to be the sum of the volumes of the wedge pyramids that we already know the volume of. So the volume, for example, of wedge pyramid 1 is just going to be the area of the base of the wedge pyramid times the height divided by 3. Which is expressed by this. And then I'm going to do the exact same thing and add up all the volumes of all the wedge pyramids, which I know how to find by their bases and their heights. Okay, and the next thing I'm going to do is I'm going to use the distributive property. I'm going to factor out the common factor of all 4 terms here. Notice that they all have a common factor of 1/3 h. So I'm just factoring that out using the distributive property, and notice that that leaves me with the sum of all the bases of the wedge pyramids. But it just so happens that the sum of all the bases of the wedge pyramids is just the base area of the pyramid as a whole. So the volume of this pyramid is just 1/3 times the base times the height. The reason I can go from this step or this formula to this formula here is because this sum inside just represents the base areas, the sum of the base areas of all 4 wedge pyramids. So combining those all together, those bases dictate the area of the entire base, or the sum of those bases of those wedge pyramids is exactly equal to the area of the base. So there's our volume of a pyramid in general. The volume V of a pyramid with base area B and height H is given by the formula 1/3 base times height. So suppose I'm looking at the Great Pyramid in Giza, Egypt. It's approximately a square pyramid, so it has a square base with the dimensions that are shown here. The pyramid's composed of stone blocks that are rectangular prisms. So an average block has dimensions 1.3 by 1.3 by 0.7. What we're going to try to figure out in this example is approximately how many stone blocks were used to build this pyramid, and we're going to round to the nearest 100,000. So since I know the volume of any pyramid in general, I can figure out the volume of the Great Pyramid in Giza. So the volume formula for a pyramid calls for the base, the area of the base, times the height of the pyramid. Okay, well, they give us the height directly, and notice that the base is a square. So the area of the square is just this side length times this side length, which turns out to be 52,900 meters squared. And we're also given the other ingredient of our volume formula for a pyramid, the height. So if I plug that into my formula, I get that the volume of the entire pyramid is 1/3 times the base, which is 52,900, times the height, which is 146 meters. Once I multiply using a calculator, I end up getting this figure for the volume of the entire pyramid. of Giza. Okay, and then what we're going to look for is we're going to find the average volume, or find the volume of an average block. They told us the dimensions of the block, and since this is a square prism, okay, or rectangular prism, I know that the volume of this prism is just going to be the area of the base times the height. Okay, well, the area of the base is given by 1.3 meters by 1.3 meters, and then I multiply that times the height is going to give me 1.183 meters cubed for the volume of an average block. Okay, so in order to find the approximate number of stone blocks that were used in the pyramid, I just take the volume of the pyramid and I divide that by the volume of each block. And once I put this into a calculator, I end up getting that the pyramid, the Great Pyramid in Giza, is composed of approximately 2,200,000 blocks. Alright, so the essential question that we addressed is how to find the volume of a pyramid and use the formula, and how to use the volume formula to find to solve problems. The volume of a pyramid in general is given by the formula 1/3 BH, where B is the area of the base of the pyramid and H is the height of the pyramid. You can use this formula in order to solve problems that involve the volume of the pyramid.